Hello everyone. In this video I will actually answer a question, like if you have an antenna and it is radiating at some frequency, and usually you would like to scale it up to another frequency or something, like for example if you implemented antenna from a paper or something like this, and then you wanted to adjust it back to your frequency range or something. So I will give some hints on what we can take care of, which parameters we should focus on, what should we expect if we are going to scale the frequency or scale the antenna to a different frequency. And for this example, I will actually take my antenna, which I designed in the tutorial 1. It is basically an antenna designed at a frequency of 10 gigahertz. And as you remember, or if you check the video, we usually design by looking at the input impedance. So for example, our antenna is, sorry, let me close this. So our antenna is like patch antenna and one layer, and then it can be fed by coaxial feeding, right? So we define coaxial transmission line, and we define the waveguide ports. And just for reference, we do this by pressing Control and the mouse. We can move in this way, shift, we can move in this way. We press shift and control together, we can just drag, okay? So yeah, so this is the antenna which we do, and for convenience we usually connect everything to the dimension. So for example, we define LPY, the length of the patch, and I connect the widths to it, and then even the location of the feeding, like XF and YF, is also some ratio from the side length, this LPY, okay? So I want to say, like, my antenna is basically or parameterized, something like if I want to scale it up or down, it will scale everything, you know what I mean? So we will see, actually, like we'll see now how it will work. For explaining this, we can go to the whiteboard. So here we want to say, like, just briefly, like the antenna is basically, as we discussed before, everything is connected to the wavelengths in some sense. So for example, if we have the patch antenna like this, we say that the length, for example, is, let's say, lambda guided over 2. This lambda guided is basically lambda of the resonance frequency divided by epsilon, almost. And this side is basically, you know, like if we call this usually L1, this is L2, so we know we want L2 to be less than L1, so we say we assume like 0.9 of L1. Okay, this is our design. And then for the feeding, we said like this feeding, it decide, it choose the impedance level or the input impedance level, right? So I'm expecting that it should be scalable, like everything should be scalable relative to this lambda guided, which is basically finally proportional to the frequency. So for example, if I want to scale to frequency F2, which is larger than F1, I'm expecting that my antenna will be smaller. So for example, it will be like L. Okay, so I'll say this F prime compared to F, right? So just for convenience. So if I want to scale to F, if I want to scale to F prime, which is larger than F, it means that L prime should be smaller than L by the same ratio. So for example, in my example, I want to scale to millimeter wave frequencies. So I'll choose F prime to be 3F, something around 30 gig, right? So we can go to the CST now. So I will define parameter, which is basically scaling parameter, for example, or make it like scale, I will say this equal 3, right? Why? Because I want to scale everything. So even the ground, if I want to get exactly the same response, right? So I will get this, I will divide by 3. Sorry, like I'll divide by scale, right? And then epsilon should be the same. So this connect to LPY. So LPY, this is the value we adjusted before. I will just divide by scale, right? It should be smaller. And what else? Dun, dun, everything is the same. And actually, as we will see later, even the dimension of the pin, also I will do the same. So it's like literally I scale everything down, you know, like so. Well, simulation is done. So we can look at the S parameters. So we see that it is scaled up almost to the 30, but around here and got wider, right? This is the first observation. And it was like this before, and when we scaled up like this. And then the reason is why, because when we scale everything except the substrate, right? So why? Because the substrate is very important to decide the fractional bandwidth, the quality factor of the antenna or something. I can explain it on the whiteboard, but I will first scale it as well. All right, and then we can let it run. And press F7 first and close this mesh. Okay, and press F7. Okay, and then we can just close the mesh. I don't know why to open it, but we can press start. And then we can see now why this happens. So when we have the patch antenna, like one way of looking at the patch antenna, for example, if this is the patch, this is the ground, this is epsilon, right? And this is epsilon like this, right? So one way of analyzing the patch generally, or any radiating element over the PEC, you can use the image, right? So this is the substrate, right? So it would be, and this is the current or something like J or M, right? So it will be something, I have patch existing on fictitious surface like this. It will be something like not existing, like we can remove this surface, and this is epsilon. We'll put again epsilon. We'll put something here like the same patch, like the image of the patch, but with opposite current. So it will be something like this and something like this. Okay, so it means like generally for any patch antenna, it can be looked at two elements of array or something with a specific distance, right? And this distance is generally should be depending on the wavelength, right? So, and then it means that if we scale everything down, we should also scale the distance, right? Because for the array to behave the same and everywhere, everything literally should be really related to the wavelength. So that's why we have also to scale the height of the substrate as well. So we'll see. I mean, like after it's done, we can see now what's going to happen after we fix the substrate height. Well, after the simulation is done, we can see the results so far. So we can see that it is exactly mapped to the 30 gig. So how we can be sure that it is exactly frequency scaling? So it is like, we can see here, for example, if you want to do the -10, right? We want almost to get the bandwidth. Roughly, it is something around 145 meg. Means that it should be here exactly scaled by 3, right? Because it's exactly frequency scaling, so the fractional bandwidth is the same. So the actual bandwidth should be multiplied by 3. So it is almost like exactly 3, right? So this is generally how we can do it, right? And then there is many things we have to consider, right, for successful frequency scaling. Okay, first, this is a very optimistic scenario because usually when you scale up, okay, so if the dimensions are very small, for example, let's say we want to scale even to higher frequencies, so we can reach some dimensions of the via or the feeding is extremely small, not feasible, right? So we have to be sure that, like we can have it as a starting point, like we scale everything, and then we just be sure that we have the proper performance, and then we have to like rematch the patch antenna. Like I will actually introduce a video, different one, for how to do this, you know what I mean? But this is just one advice, is that this you have to revisit generally if you want to scale. One thing else, it depends, like if you want to be sure, like because I will look at everything as an impedance and I will see that how it shifts. For example, if I would look at this, right, I'm expecting like, if I have some peak for the low frequency or something, right, I'm expecting that I will see the same profile of the Z parameters, right? But here we see something different, right? We see something like um, another peak, and then we are expecting here something, and then actually, like if we zoom in here, it will be we can see more, you know what I mean? It is like this is not clear if it is really frequency scaling or not, right? So the advice here, like it depends on the structure of your antenna. So here, for example, I have a patch antenna fed by transmission line, right? And then if you remember that if I have a impedance, and then always when I have a transmission line, so I have the input impedance, which is basically changing because our antenna generally here is, like XL plus RL, so it has the real and imaginary. So this gamma even, and then it is basically complex. It means that this gamma is complex, so this N is also complex. And we are sure also that if gamma is here, we know that is here something like this, right? Gamma D, right? Or beta D, right? So we know also that gamma is the same, and gamma for us is the S parameter or S11, right? So it is just the impedance profile will be different, right? So the best thing for me to do it is actually to de-embed the port. So for example, we go to the port 1, open, hold on, yeah, so it's open here in the other screen, so it's like this. So I define this de-embedding port. I do the de-embedding like this to just decide the distance to be in this direction, and that's why it should be negative. And then here, because I was having the de-embedding like 0, but I can have it like almost L pin, and minus something, so it's like the thing it will be, I can just show you after I update. I press F7. So we need to look at the port, right? You can see that I de-embedded to here. So now instead of looking to the impedance after the transformation, I will look at the impedance just like this. So I did this result, for example, for the S parameters, right? So as a magnitude, it is the same. And for real part, they are not the same. Imaginary part, they are not the same. Of course, and the phase is not the same. It's like, something like really mapping the phase or something, but magnitude is the same. The same for the Z parameter does not have to be literally the same. If you look at the real part, it is not literally the same. So when I do the de-embedding, I see different real part, right? It means that it was this value, right? And then when I do the transmission line, when I move it, the distance start to be up, large and down, large, like up and down something, because we have also an imaginary part, so that's why I'm saying that the best thing is that you de-embed, right? And then when you de-embed, I did this also, this exercise. So when I do the z parameter, the small one, I have this mode which happens from the transmission line, because if any point it happens 0, so there is the point when we have almost lambda over 4 of the transmission line length, and then it becomes infinity, right? So the same thing, if I just do the de-embedding, it starts to drag me to something else, right? So if I have this dimension of the scaling, so I have, the z input equal like this, and just when I de-embed, it actually return to something like this, right? It goes to the same impedance level, and it's just scaled, and I don't have any superior mode or something, or spurious mode for the low frequency, right? So I have just the mode of the patch, and this is the other mode of the, the other dimension. So the second advice then, it means that you better to de-embed and be sure that you only handle with the patch antenna impedance, right? So this is the two things, and scaling the height as well, because it is also like everything as we described it by the image theory. So we can discuss in the second and next video is like that when we scale up, we have the potential to have more frequency bandwidth compared to the low frequencies, because we don't have actually to scale the substrate, because we have one substrate, we want to work it out for all frequencies, right? So it means that if we want to scale, like if the things are smaller, so it's like if the patch is smaller because of the frequency is higher, it means that the patch now look more bigger, or the substrate looks more big. It means that the bandwidth could be higher. So in the next video, provide some method on how to get the fundamental bandwidth you can get from any patch antenna, and how to use the solver to be sure that this is your maximum bandwidth you can get. What are the limitations? What is the effect of the substrate as well? Thank you for watching.